In this video I will have a close look at an optical computer mouse used as linear sensor. The linear drive with the dial indicator has been used in the previous videos too. The mouse is mounted directly on the carriage of the linear drive. A print with a fine line pattern is used as underlaying surface to get a high contrast for the mouse sensor. The data is forwarded to the Raspberry Pi using an USB interface. The mouse transmits the relative movement along the X and Y axis between two requests from the host computer. The absolute coordinates are computed by the Raspberry Pi and displayed on the second line of the screen. When turning the wooden disc and so the threaded rod by hand, there is basically a change in Y coordinates. Ideally, there should be no change along the X-axis, however with that simple measurement setup, the optical sensor will never be perfectly aligned in parallel to the movement of the carriage. Furthermore, there will in fact be side movement of the carriage in the range of a couple of micrometers. The carriage is moved to 0 on the dial indicator coming from left. Now the mouse coordinates are reset to 0, and the carriage is moved to the right another turn of the indicator, which equals a linear movement of 1mm. The output of the optical sensor is 496 mouse steps along the Y-axis, which accords to a resolution of 12,600 dots per inch. That hits the specification of the manufacturer, which is 12,000 dpi. In theory, we can detect a mouse movement of just 2 micrometers. Not bad. The wooden disc can be driven by an electric motor. With an H-bridge, the Raspberry Pi can switch the motor in either direction using two GPIOs. Because of the high resolution sensor of the computer mouse, I'm using a geared DC motor to make the disc spin slowly and smoothly without overshooting. The control loop is closed through the optical sensor of the mouse. With a keyboard I can change the set point and so move the carriage. In theory, one mouse step equals a movement of 2 micrometers, but as you can see, the indicator turns not in equal steps. The reading is in the range from 0 to almost 30 micrometers. One source of error is the linkage between mouse and carriage, which isn't free from backlash. I can deflect the mouse by hand, apparently without making the indicator move. When released, the deflection is 8 steps along the Y-axis, which accords to a movement of around 16 micrometers. Same as in the previous videos, the backlash of the mechanics is measured using the home-built spring scale. We get a maximal deflection of 30 micrometers, the mechanics is adjusted tightly. Let's move the carriage to the left until 0 is reached on the dial indicator and reset the coordinates. Move 128 mouse steps according to approximately 300 micrometers to the right. And back to the left the same number of mouse steps. The resulting error is almost 20 micrometers. Let's do this again with 256 mouse steps according to almost 600 micrometers movement to the right. And back the same number of mouse steps to the left, The error is now around 30 micrometers. The result is worse than expected considering the high academical resolution of the mouse sensor. Let's modify the test procedure slightly. Again, the carriage is driven to 0 of the dial indicator coming from right, moved to the right for 100 mouse steps, thus approximately 220 micrometers with full speed, and the same number of mouse steps back to the left. When moving back, the speed of the carriage is significantly lower. When 0 is reached on the dial indicator, there are still 39 mouse steps left. Looks like the firmware of the mouse sensor can't detect slow movement reliably. Temporarily, the Raspberry Pi doesn't count down mouse steps, even while the dial indicator continues turning slowly. When the absolute value finally reaches 0, the resulting error on the dial indicator is 130 micrometers. The carriage is shifted to the left for this number of microns. Let's do another modification. Once again, the carriage is directed to 0 on the dial indicator moving to the left and the coordinates are reset. Now the carriage moves 200 mouse steps to the right, and with short breaks, thus with alternating speed, the same number of mouse steps back to the left. The error after the first run is 20 micrometers. That procedure is repeated multiple times. After 15 runs, the error has added up to 140 micrometers, now to the right, even while the carriage moved back to the left with lower average speed than it was moving to the right. On its way back to mouse 0, the sensor was accelerated and slowed down multiple times. Once more, the firmware of the image sensor seems to be in trouble detecting the movement correctly. I did some minor changes of the software running on the Raspberry Pi to display the peak relative change in mouse movement over time more clearly. While the carriage moves to the right with full speed, the relative change in Y coordinates is around 1 mouse step per loop run. During acceleration on its way back to the left, the peak value is clearly higher. Looks like the firmware adds an extra boost to the relative change in coordinates whenever the mouse starts moving. I guess that this is a feature added to the code lines by the manufacturer of the mouse. The firmware is closed source and obviously it was not written with linear sensors in mind. The specifications for computer mice differ clearly from that of linear sensors for CNC machines, which is why those devices should not come into considerations when creating linear drives. By pushing a hardware button, the resolution of this computer mouse can be changed. It is now set to 3000 dpi, which accords to the measurement. With the new settings, the carriage is again driven to the right with full speed, and back to the left with low speed. By what we get a drift to the left, same as with the high dpi setting. In the second test, the boost in coordinate change during acceleration also outweighs the lower average speed when moving back to the left, so that the carriage drifts to the right again under these conditions. My intention was to do the measurements again using a second, very cheap computer mouse. However, this device behaves totally weird. This mouse seems to be sleepy and sometimes needs more than 1mm of movement before sensing motion at all. That's what makes this device totally useless in a linear drive. You can get the measurement data and more about linear drives on the project page. Thanks for watching and I'll be back.